Welcome to this second joint event of CIBSE and IBPSA-England on airborne infection. So as we all know that the built environment has been significantly influenced by the pandemic, and ventilation in buildings is one of the crucial measures for mitigating the spread of COVID-19 and hence a huge part of the international management strategy. So today we have a range of speakers who have been working in this important topic and have contributed to our understanding of how COVID has impacted our spaces, including influencing some of the recommendations and policies on mitigating its spread and making our buildings safer. So we have 4 speakers spanning industry and academia. And our first speaker today is Professor Hugo Lee, who is a chair professor of built environment at Hong Kong University. His research includes city climate, environmental studies of infection, and indoor environment. He also serves as editor-in-chief of Indoor Air, and he has collaborated with WHO, with CDC, Hunan CDC, and Hong Kong EPD, and studied the transmission routes of SARS-CoV-2 in buildings. Welcome, Professor Hugo Lee, and I give the floor to you.
Well, thank you, Chair Lady, and thanks to all. I look forward to learning from all the other speakers and discussions with you all. My home assignment was to talk about the ventilation modeling for understanding the transmission, and I thought about and gave a subtitle and like to focus on the simple models. A lot of people to thank for, and someone gave us money to continue the work. So Professor Malcolm Cook mentioned there's a colorful things, and I also like to start with interaction between the people when you move your head and produce droplets. Our assumption is the transmission is coming from the expired droplets, and although this kind of computational fluid dynamics can offer a lot of insights, however, simple models I find to be most maybe insightful. So the model is approximation, and so I like to this should be known to you all. And there are 3 very basic models, and you might consider them, they are the first ventilation models in the history of our understanding. And this mixing box and concentration as a function of ventilation rate and air change per hour should be called Patten-Koffer-Seidel formula. So in Germany and in Japan called the Seidel formula. And I learned the chimney effect came from Piclet. The computational dynamics people know this Piclet number. And I think the turbulent jet formula, probably the first one is Tolmin. Walter Tolmin, 1945. Anyway, those are the 3 formulas I will use today. And so maybe started with because the situation in Hong Kong is challenging, and we are crowded and the rooms are small for most families. So if you have exposure of half hour or 8 hours a day to work, which one is better? You stay in a large room with less ventilation, or you stay in a small room with good ventilation? In the past, we have been discussing whether we should use ventilation rate or air change power, until I had this simple model. You basically integrate that mixed room solution into the Wells-Riley equation for infection risk estimate. And then you basically take integral and for a duration of time 30, and then the risk becomes something like this. I hope you all know this equation, and add a little extra part, which was already done by somebody in the 1990s. And this little thing, let's call it per unit ventilation rate correction factor. And then you can plot that factor on a diagram for a wide range of ventilation rates, and the horizontal axis give you volume per occupants. And then you find a very strange thing. And then that there is this dashed black dashed line across the system and for a wide range of volumes. And on that line actually is the one below here. So if I have a N and delta T are sufficiently small, but not very, very small, you do a quadratic approximation, then you find this one plus CT over QP equal to delta T over VP, the volume. And eventually you find out this whole thing, infection risk or exposure, have nothing to do with ventilation rate or change power. It actually is the volume. And so basically it says that if you look at the Ashley standard, you plot all the ventilation rate for those settings with half hour or lower, like a reception area, corridors, you find all the lines on this curve actually. If your exposure time is not very long and it's really a question of volume. It also shows that if your space is very large, huge, like a stadium, and then the ventilation rate is not important. It's some time and then it's really good. So this is why we also encourage government to place those quarantine locations into sports centers and so forth. So it's very interesting to use this very simple model to tell us quite a bit physics. And the lower the better on this diagram. Of course, the smaller this red correction factor, the lower the risk. So this is the first thing you will learn. And then for the JET model, and before the pandemic, just in year 2019, we submit this paper. Students look into this JET and then the particle deposition in the JET and inhalation. And she found out, the mechanistically, the short range airborne can be 10 times. Now using CFD, probably 2 or 3 times more important than the droplet transmission. So this is very important, and such a little understanding shows how important the short range inhalation, and that really helps to define short range airborne transmission as one of the major routes for the pandemic, for SARS-CoV-2, and probably for others too. And during the time, we learned that this less outdoor infection actually very important. I was asked in a seminar like this by a colleague at UC Davis. So how do you explain outdoor is, most the infection occurs indoors, but less outdoors. Probably for Omicron, we can have outdoors. We can discuss if you like. So then we thought, okay, you combine the steady state version of CDL solution and with a jet model, and then you find your concentration as a function of a jet, a distance from a jet, and as a function of your dilution factor. So if the steady jet, the dilution is proportional to the distance from mouth. And then you find out something interesting. If you, with some assumptions, you find if this outside at a distance 75 centimeter, then the concentration in the jet average is just 8.3% of that at the mouth. So in a room, if you give a good ventilation, 10 liters per second per person, you get 8.8%. But if you have 1 liter per second, then the whole thing increased by 50%. Very significant. So it's the first time I learned, quantified that the ventilation impacts on short range transmission. And you also shows if ventilation is good, then the infection risk in the room is very similar to the infection risk outdoors. And that's also important. That's also telling me that as long as you have light activity, 10 liters per second per person should be sufficient for, you can do more detailed analysis I will show later. But if ventilation is really bad, both long range and short range will be bad. So this is where first time I showed, oh, maybe you can use 10 liters per second per person for the earlier variant, the earlier virus in Wuhan and in Europe, maybe alpha, beta. But once you get to Delta and Omicron, then this value will increase accordingly. Of course, the real expired jet is not steady, and then you may have a puff. And you can also develop a much better model. This model now is being reviewed, and dilution is very, very significant. So this dashed line here is just following the linear, but actually it's non-linear as you move away with different activities, and dilution actually real calculation is much greater. So we compare with some experimental data, we find this dilution is much more meaningful. You are talking, actually, if you 100 fold of dilution, that's very similar to 10 liters per second per person. When you exhale, open 1 liter per second per person, 100 divided by, so 10 divided by open 1 equal to 100. So after 100 fold of dilution, then, it's basically this whole thing, dilution is no longer relevant. And so that's why with different countries have either 1 meter to 2 meter social distancing. And because of time, I will not go through this quickly. So chimney effect, interestingly, we had this many outbreaks that with distant flats, and they were infected. We had more than probably around 15 before Omicron. Now with Omicron, we have every day, there's too many now to even to be investigated. So this whole thing shows very strong evidence for airborne transmission. And we have been measuring ventilation rate in the drainage stack in high-rise buildings. And we now highly suspect the chimney effect to play a role. So anyway, with this kind of simple models allow us, 3 simple models actually allow us to understand, develop a hypothesis that the short-range airborne transmission and the long-range play the major role, and the exact ratio between 2 remains to be known, probably different for different situations. Anyway, they can explain almost all major phenomena we observed in the transmission. So I really go for the simple models and that reveal insights. So this will finish my quick talk. The simplest models, I believe, tell the real story, and poor ventilation worsens short-range inhalation risk. I believe future modeling will be more integration with human behavior and virus kinetics. Thank you very much, Chair Lady.
Thank you so much, and thanks for keeping on time. Also, I suggest that we keep the questions to the end and move on to our next speaker, Professor Malcolm Cook, who is a Professor of Building Performance Analysis at Loughborough University and PI of IBPSA project Airborne, which many of you have heard about in the previous session as well. He, in addition to completing several of the UKRI and EU-funded projects, he has also consulted for a wide range of applications worldwide, which included both the design and simulation work for healthcare buildings, schools, theatres, and libraries. So, Malcolm, over to you.
Thank you, Ruchi. Please, can you give me a thumbs up just to confirm you can hear me and see my first slide? Thank you, Ruchi. And thank you, Hugo. I absolutely concur with what Hugo said about simplified models, and I'll be talking a little bit about this in this presentation. But what I want to do is to give an overview of this project, our Airborne project, the title on the screen there, and to report on progress in each of the work packages. So yeah, I'm the PI on this project, but I am leading a very a very extensive and highly skilled team, all of whom you're able to see on the screen here, and many of whom have joined us online. So very grateful to all of these individuals and these institutions. We've also been working very closely with the DCMS, the Government Department for Digital Culture and Media and Sport, and BEIS, the Department for Business, Energy and Industrial Strategy. So our project aim there is to deliver guidance on the ventilation operation and the future design of non-domestic buildings, and to quantify the risk of and reduce the transmission of SARS-CoV-2 in buildings. Our hope is that what we learn will also help with other transmissible diseases, and also give guidance on the modelling techniques that can be used. And these are our methods. So we're really working across all of the three key research methods. We've got experimental work, computer simulation, and field work to give us the design guidance, which we're bringing together over the next 6 months or so. So I should say we're just over halfway through this project. So first of all, experimental work then. So my colleagues at UCL are undertaking work in this Class 2 environmentally controlled chamber to provide experimental data on the transport and distribution of aerosols. So this gives us a greater understanding of the transport of exhaled aerosols, and provides us with a validation data set for our computer models. And you can see the specification of the chamber there. So here are some of the examples of the tests that we've run to date. So we're looking at different types of aerosol generator. So PBS there, the phosphate buffered saline, as well as synthetic saliva, over a range of temperature, relative humidity, and ventilation conditions. The shaded boxes there simply indicate the cases that we've looked at so far. And then here are some initial results. So a time along the horizontal axis with the number of particles detected on the vertical axis. That's a number of particles at 0.5 meters away from the source, or at the chamber outlet here on the right hand side. So this shows the release of aerosols after 10 minutes, and then the variation in the particle count depending on the temperature and the relative humidity. So what we're seeing here is a clear correlation between the moisture content in the air, the relative humidity, and the particle counts. So if I take the blue and orange line here, this shows the environmental chamber operating at 75% relative humidity and 28 and 20 degrees C, respectively. And we see that for those higher relative humidities, that we're seeing a greater particle count, which is important in terms of understanding what the risks are in terms of transmission via airborne aerosols, depending on the relative humidity of the space. So out in Hugo's environment in Hong Kong in the summer with high relative humidity, there may be much greater propensity for transmission relative to, say, out in the dry desert of Las Vegas. So that's work that's ongoing in the chamber. Then I want to say a little bit about modelling. So we've got three areas of our modelling. First of all, we're developing analytical methods to develop our understanding of the physical processes. So we're looking at scalar analysis, we're looking at Lagrangian particle tracking, and we're inputting that into the detailed CFD model, which I'll talk about on the next few slides. But then just echoing something that Hugo mentioned, we've also got an analytical model where we've developed a relative exposure index model that enables us to determine how safe relative to a benchmark environment a certain space is. And I'll show you some of those results as well in this presentation. So just staying with the CFD then for a while. So what we've got here is a coupled model of airflow and human thermal comfort. So this mannequin in this simulation is a thermoregulated breathing mannequin, so it loses heat to the environment or gains heat, whatever the temperature difference might be. These are transient simulations, buoyancy driven, obviously, and a very low ventilation rate. So what we're looking at here is is how CO2 builds up in the environment. And also what we'll be doing shortly is to add particles into this exhaled breath. So on the left hand side, we've got the airspeed field, and on the right hand side the temperature, so you're able to see the plume above the seated mannequin, and then the temperature of the exhaled breath. But really what we're interested in is this CO2 distribution. I'll just, in the interest of time, I'll just go straight to the animation. So as I say, we've got a breathing thermoregulated mannequin. We're very keen on the accumulation of CO2. We're very keen on where that CO2 builds up, and are keen to look at the correlation between CO2 and particle tracks. So when we put the Lagrangian particle tracking into this model, that will enable us to gain an insight into the use of CO2 for assessing the transmission risk due to viruses. Transmission risk of viruses, sorry. So then if I just move on to task 2.3, so this is the relative risk index model which I referred to, which has been developed by Ben Jones and Chris Idden at Nottingham University, both of whom are with us this afternoon. So what they've been doing as part of the Airborne project is to develop a model based on a balance of the viral gains, the genome copies, the gains of genome copies due to emission from a person, the ventilation system, and the virus already present in the space, and how that might get diluted or removed from the environment. And there's a reference there which talks in much more detail about this model. But essentially the gains are measured in number of genome copies per second, and then the losses are arranged such that they can represent almost an air change rate. So if we divide the gains by the losses, then we get the number of genome copies, an indication of the viral load inside the space. Excuse me. So here's an example of its application to a typical school classroom with 32 people sitting there for occupying the space for 7 hours. This space is ventilated at typically they're ventilated at 5 litres per second per person, and a quarter of the time talking, 3/4 of the time not. So what we see here relative to relative to a space that's ventilated at 5 litres per second per person, which is the orange line, we see, as you might expect, how the relative exposure risk reduces as the ventilation rate increases. And many of you will be familiar with the debate over, well, if I increase the ventilation, I'm going to increase the heating load. There are risks of occupant discomfort. But what this model enables us to do is to really start to quantify the benefits or the disbenefits of increasing ventilation flow rate. So as you can see, it's an exponential relationship. So even though we do reduce the risk of transmission, the rate of that improvement increases in the manner you can see there, and at a rate that you can see there. So of course, our attention as modelers and as people wanting to make a difference to the safety and the indoor environmental quality of our occupied spaces, our focus is in here. As you start to reduce the ventilation, or as people choose not to open the windows, how quickly does that relative exposure risk increase? And we can, using this model, we can actually quantify the increase of that risk. Moving on to the field studies, so we were very fortunate. We were tied into the government's events research programme, working, as I said earlier on, with the DCMS and BAYS, involved with Wembley Stadium, involved with the famous nightclub event in Liverpool, plus some corporate conference events, as well as semi-outdoor festivals. So this picture on the bottom left here shows my colleague Ben Roberts at the Download Festival installing sensors, which is actually about 5 miles north of Loughborough, near to East Midlands Airport. So this work was led by Leora Melky-Epstein and a team at UCL, yeah, she coordinated this massive task of, and I won't remember the numbers, but hundreds of different spaces and tests across the country. So this was a mammoth undertaking for our team. So this is about assuming that CO2 gives us a good indication of ventilation performance. Now we know that CO2 may not be directly equivalent to SARS-CoV-2, but we do know that CO2 is exhaled along with water vapor, and that these viruses live on water particles. And part of what we do in AirBods will be to draw this comparison between CO2 dispersion and the dispersion of aerosols to really give some insight into the benefit of into the accuracy of using CO2 for assessing this transmission risk. But certainly we were able to use CO2 to give us an indication of the likely ventilation performance of the space. And we did that by looking at instantaneous CO2 levels, shown here in the third column, and also multiplying the prevailing CO2 levels with the time that those concentrations existed to give us this total cumulative exposure to CO2, and using that came up with this exposure classification from A to G. And you can read much more about this in the documents, and I'll leave you with those references at the end. But just running through some images then. So I mentioned the nightclub in Liverpool. This was a very, very large space, so 160 meters plus in length, and naturally ventilated, essentially from one side. This shows the sensors that we used. We were very nervous about this installation, thought that very few of them would come back, but I have to say my confidence in the people of Liverpool has been fantastic in terms of this. We got all of the sensors back. It was great. So some of you may have seen that on the front page of the newspapers when we were undertaking this work. Just as a context, so here are our sensors along the edges of the space. With more time, we could have done a more detailed risk assessment, and we could have had cherry pickers in there. But what you've got to remember is that Leora and the team were setting this up in a matter of hours and days to make this happen. So we did what we could and did a good job, of course. Yeah, have I got to finish now? Yeah, okay, thank you. So I'll just say then, so in terms of the CO2, levels, it won't be surprising for you to hear that the CO2 levels were higher on this side of the space than they were on the side where the openings were. So the single-sided ventilation meant that we were having a problem with crowding over on this side in terms of the CO2 levels, and they're shown in the graphic here. So I'm going to have to finish up here. This was a much more formal environment, lower occupancy, and unsurprisingly, CO2 levels much lower, and a space where we understood the ventilation much better. And that's what we found. So it was surprising the number of building owners we were working with who didn't understand how their buildings were intended to be ventilated. Understanding the plant, understanding when it was last renewed, commissioned, etc., is one of the incidental outcomes of the project. So I'll just finish here in terms of, so what we're doing now is to gather all of this information together, do a bit more CFD modeling, and develop our design guidance and dissemination. Do please visit the AirBods webpage, where we've got a list of publications showing a lot of the data that I've just been presenting to you. Thank you very much. Thank you, Ruchi.
Thank you, Malcolm. And I see questions coming through the chat, many of them. So I will quickly move on to our next speaker so we can have some time at the end for Q&As. Our next speaker is Fred Mendonca. He is PI in a project, UKRI project called Vent Easy, which assesses also ventilation interventions towards indoor air quality and pandemic resilience using CFD. Fred is a graduate of Imperial College and is currently working with the open source code OpenForm and honorary professor at Exeter University. Over to you, Fred.
And thanks a lot, Ruchi. Can you just give me a sign that you can hear me and see my screen?
Yes, we can hear you and we can see your screen. We don't see you, but yeah.
That's brilliant. So thanks to the organizing committee, Ruchi, and for the invitation to speak here, really as a follow-on from the first event in this series, which was last May. So I'm really happy to be able to give you some kind of culmination of this UKRI project sponsored by Innovate UK. Really looking at purely simulation, but also supported by validations and field measurements to give us some confidence that the simulation in a full in situ is working in a way that is really usable with respect to moving forward to the next steps of ventilation and infection resilience. So it's really nice to be able to acknowledge the work, particularly of my colleague Pawan Gildial. And with that, let me just move on to the next slide. I'm going to take the baton from what Malcolm just said. It's surprising how many building managers don't really know how the ventilation in their buildings work. So that's an absolutely wonderful introduction to this next slide. I'm sorry about the fact that it's very, very busy. This is really summarizing what has come from the Royal Academy of Engineering initial report on infection resilience environments. So the motivation essentially is coming from the National Engineering Policy Centre here in the UK, coming from questions asked directly by the top of government, right up to Sir Patrick Vallance. So here's what the evidentiary hearings essentially came up with on the basis of interviewing several building managers and estates managers. And it's really quite surprising or even shocking, the kind of evidence that we're hearing. The UK building industry and maintenance industry is not achieving what it needs to with respect to air indoor quality. It's truly shocking, the lack of understanding and interest in what we run. It blows me away. I don't know what good ventilation is. When it comes to transmission methods, fomites, droplets, aerosols, these are a huge mystery. Telling people that we have to increase our air supply to 16 liters per second means nothing to the average office occupant. So it really sets the challenge very well indeed in respect of, you know, all the work that the researchers, the scientists, the engineers are doing, really to bring this on the ground and make it really truly valuable for everybody that, as we all do, are occupying buildings kind of every minute of the day, every day of the year. So it's good to be able to share with you some stakeholder experiences in several kind of real application areas, where we're beginning now to counter those initial thoughts, to the point where people are now confident to proceed with simulations to reassess the ventilation. In certain other analyses, these analyses of airflow and understanding the problem allowed us to de-risk a number of significant areas of concern. And more to the point here, provided a body of evidence to chief scientific officers. The other thing with respect to fluid dynamics is you can't really see the fluid moving, but with simulation, being able to choose imagery, so well-chosen imagery and plain language, makes the benefits tangible not just to professionals, in this particular case, education, but also to the peripherals, the children themselves, the parents, governors, etc. Another testimony is coming from healthcare sector, who are now feeling that they're in a position substantially to shorten their inter-patient treatment times, so-called fallow times, which reduces clinical waiting lists. Being able to visualize airflow, circulation, and thermal environments brings significant insights. So, you know, we feel as engineers a little bit like the cavalry coming over the hill, the knights in shining armors, showing how to use engineering really practically for the everyday environments that we find ourselves in. So I'd like to just give you some examples here of some of the stakeholder studies. The first one is really to do with validation. So we're sitting in a fully occupied and equipped office environment. The office here is actually the head office of the Elta UK fans in the UK. Its occupancy about 25 people dotted around the main office that you can see on the top right there, and the schematic on the bottom right. And essentially what we're doing is taking full kind of detail of geometries, equipment, computer equipment, heat sources, heat losses to the exterior, ventilation, etc., in really full detail, including breathing cycles, breathing with or without a mask, talking loudly, all sorts of variants there, and trying to compare those in terms of then real validations in terms of humidity and CO2 and temperature measurements. So on the right-hand side here, if you can see my cursor, is an actual set of measurements of the CO2 level during the day. On this particular day, which was the middle of July last year, during the morning, obviously the CO2 levels have recovered down to very low levels, or background ambient. And then as people start to enter the office, it climbs up to around 600 ppm. There's a slight dip at lunchtime and then recovers back up to the same kind of steady level, and then goes back down to background levels, or the environmental levels once the people have left the office. So you can see from these measurements, we can approximate a steady state in the office at around 600 ppm here. This particular sensor was put in the middle of the office, the yellow space that you can see there. So we're plotting this at the height of the sensor itself in the room at that level at about 600. It's also taken at 2 different locations through to where the sales team is talking quite a lot. So the CO2 levels locally in the office are higher. And also in a small single occupancy office where you'd expect the CO2 level to be lower. And that's the green dot there. The continuous lines are continuous CFD prediction lines across the height of the room from the floor up to the ceiling. And you can see that it really correlates extremely well with the measurements. And this is now simulation, more or less a black box, out of the box, which gives us a really good level of confidence with respect to validation, and now using these methods to be able to change our design specification or the design effectively to be able to make the ventilation fit the occupancy. Okay, I'll go on to my next example, which was activated on very early in the COVID epidemic. So the Department of Health and supported by the military in the UK were asked to fit out what's called mobile processing units. So these are the backs of the vans or trailer units, which were then equipped with these very, very important piece of equipment, microbiological labs units and lamp processing units. So these are rapid testing and rapid results processing of the samples for COVID testing that were taking all over the country. So around 30 or so mobile processing units were commissioned. And this is really showing a pre-design prior to the commissioning of those units in terms of the CFD used for the thermal environment to make sure that the equipment was running in a good state, and also that the occupancy, these are the operators here, were in a good thermal and a good ventilation environment. So you can see that ultimately they were able to de-risk a number of significant areas of concern. The real point here was to provide evidence to the Chief Scientific Officer in the NHS that the platforms were developed appropriately. So that's in terms of design efficacy. Let me move on to kind of experience or deployment in real world circumstances. So this is an example of a church gathering hall. Essentially, it comes from the London Archdiocese of Southwark, which has a footfall of around about 1,000 people every weekend. The advice from the government, the advice from the Archdiocese was open your windows and doors. That's the way you mitigate against COVID transmission. So they were concerned that just opening windows and doors, how did this practically affect or reduce transmission potential? So these simulations were able to show that when opening the doors and the windows, especially in this winter condition, that you see here from the animation that cold air pours in to the space from the windows and the doors, and then spills in and kind of fills up and covers in terms of fresh air penetration, especially the area occupied by the people in this particular space. So this is now telling us, if you watch the ISO contours, that it covers the people really within 5 minutes, 300 seconds. So within 5 minutes, this is now demonstrating that the occupancy is getting a single fresh air charge every 5 minutes. That's equivalent to about 12 air changes per hour. Okay, moving on to healthcare and treatment rooms. This is now a detail of looking into
2 minutes, Fred.
Okay, that's great, thanks. It's looking at a detail of mechanical ventilation coming from a hospital treatment room, enhanced by mechanical ventilation. So in this particular case, only 5 air changes were coming from mechanical ventilation, and it had to be enhanced by certain devices. And the enhancing by certain devices also enables to give you some idea of droplet clearance. So when an AGP, so-called aerosol generating procedure, generates droplets, we're able then to track where these droplets are going to go in space and how quickly they will reduce to a small percentage of the initial number of droplets. So my final example here is an education center. It's a primary school in Merton in southeast England. It's quite close to a Met mast, which was measuring the average wind speed to be coming at about 8 knots in a southwesterly direction. So under these circumstances, what we're able to do is offer simulations of the external wind conditions coming from Met Office data with windows opened, and then to compare those with a still day device on, air cleaning device on, with windows open and closed. The real value here is in terms of best practices. So this particular study led to standard operating procedures for every classroom in the whole school, where the teachers were able then to balance the monitors that the Department for Engineering have been giving them in terms of CO2 levels. And when they see those CO2 levels rise beyond, let's say, an acceptable level, they know exactly from these standard operating procedures in every classroom which windows should be opened and which windows should be effective. So my final slide here is really the same slide as I closed in the last presentation. It's saying that, you know, we know CFD has been effective and validated for the past 50 years. What we're now learning to do is to apply CFD to ventilation, to be able to measure, mitigate, and optimize ventilation within enclosures. And there are very many tools now out there to be able, in this validated space, to help, you know, those building engineers, those building managers, effectively to change or to adapt their ventilation to give the strongest resilience. The conversation is moving away from COVID, and it is moving towards air quality, ventilation, and infection resilience. So I think with these examples, we have a really good set of examples and confidence that we're moving in the right direction. So Ruchi, thanks for your time today, and I'll pass back on to you. Thank you.
Thanks very much, Fred. We have, again, questions coming in the chat. We won't be able to go through all of them, but let's try. So I'll move on to our next speaker, Carolyn Gurio, who is working on the CoTrace project at the Civil and Environmental Engineering Department at Imperial College. Her work focuses on assessing exposure and infection risk in naturally ventilated classrooms. So nice continuity from the last talk. Over to you, Carolyn.
Thank you. Thank you for the introduction and for the invitation to talk today. I'll try and be quick so we have time for questions at the end. I thought it'd be a good start by describing the CoTrace project I've been working as part of. So this is a project between the universities of Cambridge, Surrey, and Imperial that aims to look at how to reduce the spread of COVID-19 in schools. So this has been done through several work packages. The first one is scaled lab experiments, and you can see an example here. And this has been done by the group of Paul Linden in Cambridge. We've also been doing CFD simulations as well. So I'll be showing a few of mine later on. But another of our colleagues have been working using IC1st at Imperial. So this is a team led by Chris Payne. We've also done quite a few field measurements that has been done in Surrey by the team of Prashant Kumar. And they've been going into schools and classrooms and doing measurements for up to 2 weeks. And they've done both summer and winter campaigns, as well as more detailed measurements using several sensors in the same classroom. And the last work package I'll mention as well is one focused on risk prediction and how to infer risk in classrooms. We've also tried to work on how to make this work accessible to a wider audience, and specifically to teachers and school leaders. So what we've tried to do through our CoSchools website is to develop tools to help with the DFE's CO2 monitor rollout in schools. So you might have probably heard that these monitors have been distributed in all schools around England to help with ventilation during the pandemic. And what we try to do with those videos is really to help and empower teachers so that they know why those monitors are useful, but also how to best use them and how it might help both in the context of the pandemic, but also more widely to help with indoor air quality and the focus and learning of their students. So the videos are available online on this website, along with some additional material to really help with teaching, helping teachers know what to do. I was going to start to talk about the first kind of work I did as part of this project, which was to look at how to infer risk and from airborne transmission of COVID in classrooms using CO2 measurements. So I think this was presented in the first part of this event last year, so I won't go into too much detail. But basically what we did is we adapted the work from Rudnick and Milton and used CO2 measurements to infer the risk of infection, so calculating the number of secondary infection that might arise when a single occupant is infected and keeps attending the same classroom for 5 work days. And what we managed to do this by using kind of a historical pre-pandemic CO2 data from 45 classrooms around England. And what this showed, which is quite interesting, is that the risk is highly dependent on the season, which is what those graphs show here. And basically, only considering changes in environmental conditions and the ventilation, we can show that there's a much higher risk of secondary infection in the winter months, so in the colder months, compared to July, which is the least risky month. And what this work, the question that arose from this work was how valid was a single point of measurement of CO2. So in those measurements, we relied on the CO2 sensor that came with the ventilation system. So what we wanted to do next was to use CFD to check how valid this single point measurement was and how good CO2 would be as a proxy for far field exposure to infected breath. So what we decided to do was to really focus on the effect of ventilation on the distribution of CO2 and infected breath. And we wanted to look at a case where it might be hard to have a well-mixed room. So we decided to focus on a buoyancy-driven ventilated room through high and low level openings, so displacement ventilation. And this is kind of the simplified setup we ended up on, where occupants are represented just purely through the heat they generate, and that heat is inputted on the floor along with the heat needed to heat up the room with radiators. And this was done using open foam and run simulations. As I said, the flow here is buoyancy driven solely, so we're not imposing any kind of flow rate at the openings. And the only way we're, the way we're inputting CO2 and infected breath is through passive scalars, just at a breathing height. So we designed this ventilation setup to provide a comfortable environment to occupants. And we also looked at 2 configurations, one where the openings are on each side of the room, so this kind of cross flow case that you can see on the left, and one where single-sided. What we realized quite quickly is that this is quite a challenging thing to do with CFD. Naturally ventilated rooms are quite hard to simulate for a number of reasons. One is that you have to use pressure boundary conditions at the openings. So if you make a wrong choice, it can directly impact your flow field and therefore your CO2 results. You also have very large scale fluctuations, which means that you have to use a transient solver. And then the initialization is very important because we found that you could have different steady states. I wanted to go through a few of the results that we've had. This is particularly interesting. So I think counterintuitively, we thought by having this single-sided, so this bottom ventilation setup, this would lead to worse ventilation. And what we realized is how we've set up the case, this is actually not the case. So what you can see here is the streamlines entering through the inlets and then kind of flowing across the room and back up. The colors show the age of the air, so the more reds, the older the air is. And what happens in this case is that the single-sided setup is actually a lot better ventilated, and in the cross flow you have a big region where the air is quite stagnant. And although this doesn't really affect the bulk flow rate or the room average temperature or the temperature profiles, as you can see here, it has a big impact on what happens to the CO2 distribution, both in terms of the room average CO2 and also the distribution across the height, as you can see here. A question we also wanted to look at was, if you were to use a sensor, where should you put it in the room so that it's representative? And so a way we've been thinking about this is looking at those PDFs. So on the left is the overall room CO2 distribution. The blue PDF is across the whole room, and then the red is if you measure close to the wall, so maybe where you would naturally put a sensor. And what this has showed is that if you're above the breathing height, it is broadly representative of what you get in the whole room. And then to go back to this first study that I showed, looking at seasonal variation, we wanted to think about how valid CO2 was as a proxy for looking at far field exposure. And this we did by introducing different passive scalars at the same level at that breathing height and comparing them with CO2. So we introduced different ones to look at the effective position. And we could then compare the actual exposure, so to that infected breath, with the proxy exposure that you can infer from CO2 measurements. And I should say, we focus here only on the far field. So this white square is where the infected person is, and that's what we say is their near field. And what this shows is that actually using CO2, your proxy exposure is within a factor 2 of the actual exposure. So it's not that bad in most of the breathing plane. So I just quickly wanted to finish this talk by saying that, so this work is going to continue, and is going to continue as part of the SAMI project, which starts in August. So this is a continuation from CoTrace. And on top of that, we also plan to deploy more than 2,000 CO2 sensors in schools, and also kind of add a behavioral and citizen science aspect to the project, to develop a web hub, both to collect the data and also share it with the schools where we've been collecting the data, so that students can have a look at what happens in their own classrooms. So thank you.
Thanks very much, Carolyn, and thanks for keeping to time. We have 4 minutes left. So I took a quick look at the Q&A, and I would like to invite our speakers maybe to give their opinion, because there are a lot of questions coming in about the design of the ventilation system. So single-sided versus multiple sides, how much that's been considered in the studies that you have shown, and its importance relative to the ventilation rate. So I don't know if that summarizes a number of questions that have been. Malcolm, you have your.
Yeah, okay, I'll chip in. Yeah, I mean, it's a lot of what we've discovered, and a lot of the points raised in the chat, which are all highly relevant points, are about concerns we've had with ventilation for a long time, and things that we've known. What's the key thing here, and the place where I start my lectures with students, is you can't see the air. You don't know whether you're getting adequate ventilation. And unless you've got a CO2 monitor, you don't know how stale or fresh the air is. So, what I'm hoping as a result of the work that all of us are doing here is that we just start to respect ventilation. We start to respect air, and we start to respect how we design for it. So I think it was Andrew, I forget his surname, sorry, Andrew in the chat was talking about old leaky homes, and they were airy, etc. We moved from that to trickle vents, and there just seemed to be no respect for the need for air, not just for combustion, but for just existing and well-being. So Ruchi, you moved on to the design, I think, and yeah, I mean, I acknowledge what Hugo said about the need for ventilation rates, but at the same time, you've really got to, I don't think we do enough, certainly in this country, to address ventilation effectiveness. I think ASHRAE have got some interesting guidance in their 62.1. That's primarily for mechanical ventilation though, and I think we need to do a bit more here in terms of just giving guidance on how effective single-sided ventilation is relative to say mechanical displacement, etc., so that designers and operators of buildings know how to create healthy environments, and how what they do might degrade that environment.
Yes, I know that you also mentioned that the problem of single-sided ventilation in Hong Kong, but I think that's even true for Europe. Most of our buildings and spaces don't have double-sided ventilation, and that potentially does become a problem. I don't know if you, Fred or Carolyn, in your experience with schools or studies.
Can I chip in there?
Yeah.
Yeah, for us, the experiences over the past 12 to 18 months has really brought an understanding that what experts understand in terms of ventilation. And I think broadly experts agree what ventilation is and what it does. What we've done now is to broaden that discussion to non-experts. So those who have never had an idea of ventilation or airflow are now beginning to understand its importance. And just with that awareness, I think it's a very important dialogue to have. And the building of awareness will naturally take us to a direction where we're beginning to increase better, reduce infections, etc., simply because of the general awareness among non-experts. That's the biggest learning, I would say, for me over the past 18 months.
Thank you, Fred. I'm afraid we've run out of time. We will have to close the seminar now. But what we can do is, given the set of interesting questions that have come in, we can compile these and upload them on the website, and we can invite our speakers to respond to some of these questions and put them up in a week or so. So thanks everyone for joining, and I look forward to seeing you virtually next time at our next session. Thank you so much to our speakers.
Thank you.
Thank you too.
Bye-bye.